Hey guys, what's up? This is Monroe and I'm bringing you another video. Today we're going to go over Markov chains. We're going to go over what is a regular Markov chain, why is it regular. Then we're going to go over a problem with a two-state Markov chain where P and 1 minus P needs to be found. And then at the last moment we're going to go over a problem with a probability distribution already given to us about cars and where they're located at. So basically we're going to start off with the Markov chains. And what is a Markov chain? A Markov chain is a matrix. So this is a Markov chain, right? It could be any matrix, any size. I believe they have to be square, but I think most of them are square. And I'm not sure about that part. And I know that, that's all about you need to know about Markov chains, really. Now, we're going to go over whether a Markov chain is regular or not. And for those of you who are watching me and you like to watch me because you just like to hear me talk, well, for you guys, I'm sorry I'm not doing gaming videos like y'all want me to, but eventually I will get there. Alright, so we better start this off. The first Markov chain we have right here, this is, let's see. First of all, let me go ahead and read the question. It says, which of the following matrices are transition matrices for regular Markov chains and why? So, if I zoom in right here so that y'all can see this really clearly, the first matrix is 0.5, 0.5, 0.5, 0.5. Now, for this matrix, God, that looks terrible. 0.5, 0.5, 0.5, and 0.5. And I excuse my handwriting. This is a Markov chain. So, therefore, these add up to 1 if you add up the rows. And nothing really special about the columns, and because they represent probabilities. So like this is state 1, this is state 2, this is state 1, this is also state 2, and this is the probability that it goes from state A to state A. This is the probability that it goes from state A to state B, etc., etc. Anyways, so if we want to find out whether a Markov chain is regular, then some power of the matrix has to be strictly positive. So that is strictly positive. That means no zeros and no negative numbers can exist in this matrix. Well, I've already done out the calculations for these matrices, and I'll explain even more later on for a more complicated problem in problem B. And let's see, if we square this matrix, so this is T. If we square T, that means take the column and multiply by the row, and that'll give you, like, if 0.5 and 0.5 times 0.5 and 0.5 will give you this entry. Then you do it for this column times this row, and I'll give you this entry. Then this column times this row will give you this entry, and then this column times this row will give you this entry, which will give you another 4 by 4 matrix. All right, so T squared, I already calculated that. That's going to be 0.5, 0.5, 0.5, and 0.5. That is a regular matrix, because the definition of a regular matrix is that some power of the transition matrix is a strictly positive matrix. The second power, the very first try that I had with this matrix, gave me a strictly positive matrix. Therefore, it has to be regular by definition. Alright, so that goes for problem A. Now problem B, you can see it right here. It is 0.5, 0.5, 1, and 0. Now, I'm not going to go through each one of these and write them out and then show you the multiplication, because I mean, a fifth grader can do that. So I'm just going to go ahead and tell you that for this one, t squared is equal to 0.75, 0.25, 0.5, and 0.5. Therefore, since the second power of this matrix is a strictly positive matrix, there are no zeros, there are no negative numbers, therefore it is a regular matrix. Regular matrix. Regular. In my terrible ass handwriting. Alright, so that goes for that problem. And I'm going to go through these problems really quick because they're easy. They're very easy. So this matrix is a little bit more complicated. It's oh, did I say B earlier? That's not the complicated one. C is the complicated one. All right. So we got a third, 0, 2/3, 0, 1, 0, 0, 1, 5. I mean 1 over 5 and 4 over 5. So I'm going to say t squared is equal to 1/9, 2/15, 34 over 45, 0, 1, 0, 0, 9 over 25, and 16 over 25. And I did not calculate this by hand. I used one of these. I think it's this one. I used this in order to calculate my matrix. Anyways, so let's see here. And if you want to go to that link, it's right here. So just go ahead and it's matrix.reshish.com. You don't have to do the slash part. I mean, and if you still can't find it, just Google it. It'll be there. Okay. So anyways, I used matrix.reshish.com to calculate t squared. I mean, t to the 20th power, which I can actually do that right now for y'all. And let's go ahead and full screen this. Yes, I have a lot of tabs open. You're gonna have to excuse me for that. Let's see. This is a 2x2. No, 3x3 matrix. No, that's not what I want. And I'm gonna look at power 20. Let's see where this thing goes in the long run. Like, does the middle row change its values? That's what I want to know. So let's see. We're gonna change this to fractions. And 1 over 2, 1 over 2, 0, 0, 1 over 2. Is this really the matrix? No, it's not. What am I copying? Oh, whoops. My bad. Alright, so let's see here. Excuse me, guys. I was copying the wrong matrix. That's the next problem. Let's see. This is 1/3, 0, 2/3, 0, oops, 0, 1, 0, 0, 1 over 5, and 4 over 5. And as I said earlier, the rows, if you sum them up, they sum up to 1, so it's really easy. So if you look at this, t to the 20th power is going to be a really small number, I don't know what that number is. Anyways, I don't know what that number is, but they're not 0. Anyways, and this one stays the same, and so does this value. Therefore, this value, and this value are going to be not strictly positive, which is going to cause for this matrix right here to become a non-regular matrix. So this is non-regular. All right. Now let's go to the last problem. Problem D. I don't know why he put this point here, but you know, it's whatever. Anyways, I'm gonna just go ahead and tell you I calculated t squared, and it was 1/4, 1/2, 1/4, 1/6, 5/12, 5/12. If you can't tell, this is kind of boring to me, but you know, I figure someone might benefit from it. 5/18, 4/9, and 5/18. You can all see that there are no zeros and all of the numbers are positive. If you want, you can go through and calculate and make sure that they add up to the right, that they all add up to 1 on the rows. 5 plus 8 plus 5 is 18. 18 over 18 is 1. 2 plus 5 plus 5 is 12. 12 over 12 is 1. 1 plus 2 plus 1 is 4. 4 over 4 is 1. And if you don't know how to do that, you should probably look up a video on fractions and common denominators. So, because this is not what the video is about. All right, now, now it's time to get this back on here. See how much we can blow this up without losing any words. Yeah, it looks like this is it. Right there. Okay, so problem number 2. Now, this is where stuff gets interesting. Problem number 2 says a certain experiment is believed to be described as by a two-state Markov chain. And what does that mean? That means this is state 1, this is state 2, like this row is state 2, this row is state 1, and like it goes from state 1 to state 1, state 1 to state 2, state 1 to state 2, state 1 to state 2. Wait. What? Okay, from A to A to B, B to B to A, and B to B. So those are the different states. I think I fucked up the last one, so don't listen to me. I'm relatively new to this myself, but I know what I'm doing. Okay, so, and anyways, when the experiment is performed many times, the chain ends in state 1 approximately 20% of the time, and in state 2 approximately 80% of the time. Compute a sensible estimate for the unknown parameter p and explain how you found it. Okay, so what we're going to do is we're going to write down here this matrix, 0.5, 0.5, p, and 1 minus p. That's our t. We want to evaluate t to the n power when n is large. So we want to see what that is, but we have no idea what to make it so that 20% of the time you're in state 1 and 80% of the time you're in state 2. State 1 is this column. State 2 is this column. So state 1, state 2. We want those to be equal to 0.2, 0.2, and 0.8, 0.8. So I fooled around with this a little bit, and let me show you exactly what I did. And let's see if we can make this infinitesimally small. Yes, that's what I used to record Audacity. Let's see how much we can do this. All right. So we're going to go to matrix power right here. We're going to do a 2 by 2 matrix. We're going to put it on power 100. Let's do that. All right. So I'm going to put this as decimal. I'm going to put 0. Oh, what? We're going to put 0.5, 0.5, 0.1, and 0.9. The reason I know that it's 0.1 and 0.9 is because they have to add up to 1. Yada, yada, yada. It's really easy to do. That's why this is 1 minus p. And anyways, we're going to calculate that, and we get 0.16666 repeating, and 0.8333. So that means we were pretty close, just with our first guess. But it's not quite enough because we want this to be 20%. These two values, and we want this to be 80%. These two values. So what we're going to do is we're going to go back to matrix power, and we're going to do power 100 again. And I did this with power 20, so I might have been wrong in my answer. 0.5, 0.5, 0.15, 0.85. Now we're going to calculate that, and we get even closer. But this time we went too far down and too far up. So we want to go back again, and we want to try another one. Like, I don't know how to do this in any other way, so if you do know how to do this any other way, it would be really grateful if you let me know. Anyway, so I divide it by half. So I, like, instead of 0.05, I do 0.025 and 0.875. I calculate that, and bam, we got 0.2 in this column and 0.8 in this column. So that's what our values are. Oh, damn, I didn't mean to do that much. All right, let's go right there. All right, so now we learned that P is equal to 0.125, which makes this 0.875, and that was our answer. It took me hours to do this problem because I was trying to do it with t squared because I was trying to do it by hand. If anyone knows how to do this by hand without using anything else, I mean, and don't be smart and say, oh yeah, just multiply it out 100 times, because I would like to see someone do that, because I ain't doing it. All right. Finally, we have the last problem, which is the day-by-day. Oh wait, hold on. The day-by-day car rental agency only rents cars on a daily basis. Rental cars can be returned at the end of the day to any agency's 3 locations, A, B, or C. If a car is rented at location A, there is a 20% chance it is returned to B and 10% chance it is returned to C. If it is rented at B, there is an 80% chance it's returned to B and 10% chance it's returned to A. If it is rented at C, there's a 60% chance it's returned to C and 30% that's returned to B. All right, and then the first question asks, what is the transition matrix for the Markov chain? All right, well, that's actually pretty easy. It's actually fairly easy. And let me show you how to do this. So, let's see, I need to make this smaller. Okay. So, first thing that you want to do is you want to make a matrix with the states. There's state A, state B, and state C. What this means is that the car is at A, the car is at B, or the car is at C. And it goes to either A, B, or C. Alright, and the probability that it goes from state A back to state A is not given to us. But it is given to us that it's a 20% chance that it will be returned to B if it's from state A. It's also given to us that it's a 10% chance it will be returned to C. Therefore, this has to be 0.7 or 70%, because it needs to add up to 1. The row does. So next row is B to A, which it is not given to us, but it is given B to B, which is 20% chance. No. 80% chance that it's returned to B. And a 10% chance it's returned to A. Oh, it was given to us. And that makes this 0.1 as well. And for the last row, if it is rented at C, there's a 60% chance it's returned to C. So 60 here. And a 30% chance it's returned to B. And at least 10% chance for A. And bam, we got our transition matrix. That is our transition matrix. So what do we want to do with this matrix? Where's the eraser? Where's the eraser? What the? Oh, here it is. I really wish they would have made this a little bit bigger. Anyway, so you know that's T. Don't have to waste my space. All right. Now we want to show if 10% of the cars start in A, 30% start in B, and the rest start in C, what is the distribution of cars after 2 days? Well, it just so happens that if you have a distribution U, so if you have U, which is the starting distribution for a population, then U to the N, which is the population distribution after N steps, is equal to U times the transition matrix to the nth power. So this says that the probability distribution after N steps is equal to the probability distribution, the starting one, multiplied by the transition matrix after N steps, or N transitions, whichever one that you want to call it. So I already took the liberty of calculating this for 2 days, T squared, and you can do this on your own, is equal to, well, I'm going to go ahead and move that text right here to a different location. All right, and so the transition matrix is, for T squared, is 0.52, 0.33, 0.15, 0.16, 0.69, my favorite number, 0.15, 0.16 again, 0.44, and 0.40. Bam. Now, U in this case is our starting distribution, and that is 10% of the cars start in A, so that's the start. I'm going to let this be A. And 30% start in B. And the rest start in C. That's our starting distribution matrix. So it just happens that U times T squared, since this is a 1 by 3 matrix and that's a 3 by 3 matrix, so 1 by 3 and 3 by 3, E's cancel out, and you get a 1 by 3 matrix back, which should tell you the probability for A, B, and C. Now I don't know what happens if you switch these numbers around. This is column A, so I made this column A. This is column B, so I made this column B. And this is column C, so I made that column C. If I switch them around, I don't think it'll be the same numbers, but you can try it all on your own if you're curious. So anyways, UT squared is equal to 0.196, 0.504, and 0.3. What this means is that 19.6% of the cars are in 2 days were at A, 50.4% of the cars were at B, and 30% of the cars were at C at the end of 2 days. Alright, so now we're going to problem C. In the long run, what percentage of cars will be in each location? And I'm assuming that they want the same U. So I calculated U to the T20th power using the software that you saw before. And it just so happens that if you do that, you have okay, well actually let me start off as T to the 20th. So T to the 20th is equal to 0.25, 0.55, and 0.2. Come on, can't you give me a little bit better than that? Okay, whatever. Alright guys, I'm sorry. Just give me 1 second. There we go. And these repeat going down. And then U to the T20th power is equal to 0.25, 0.55, 0.2. Therefore, in the long run, 25% of the cars will be at A, 55% of them will be at B, and 20% of them will be at C. Alright guys, if you watched my video for 30 minutes, I really appreciate that. You now know about Markov chains. You now know how to make transition matrices. You know how to tell if a transition matrix is, or matrix I meant, is regular. You know how to approximate a Markov chain with a certain percentage of values lying within a state, and you learned a little bit about how to use computer software to help aid you in this endeavor. If you want to see more videos, make sure to click that like button and subscribe to my channel. I will be posting gaming videos later on in the year, probably this year. And everyone have a wonderful day. It's been nice. I enjoy doing these videos, and I will do my best to crank them out as fast as I can. Alright guys, have a great night or day.